Hi, so I'll introduce myself. I'm Guillaume Zoppi from Northumbria University, and I will present today kind of a short presentation of the activities that we've been doing as part of NECEM. Our project was energy capture and transfer on scalable substrates, or acronym ECATSS. I think I'll only pronounce that once. And the aim of the project was really to create a null solution, efficient and earth abundant thin film solar cell. What we are looking for is techniques that are highly scalable in terms of area of fabrication and power, low cost, low manufacturing footprint in terms of carbon, possibly high efficiency by the choice of materials, and also ultimately to be able to use non-flat surface. So as a work plan, I'll go through our device platform, what we've done to reduce disorder in our material, what we did to improve our PN junction, and a little bit about our flexible substrates work. So the platform for us is we use nanoparticle inks made from metal salts reacted in solution, and we create small nanoparticles. So those nanoparticles are made of copper, zinc, tin, and sulfur, and the method is called hot injection because that's how we introduce sulfur in our metal salts. Following those, the production of those nanoparticles, we fabricate inks, which we then deposit on a substrate. If we're going to stop here, the device, the solar cell, will not work. So we have to do what's called a recrystallization process, in which we react and we anneal our nanoparticle film with selenium to form large crystalline grains. And then we fabricate a device either on a glass substrate or on a flexible substrates. So this is just to give an overview of our process. The first part of the report I want to present is some of our new insight into the selenization process. So this is that selenium to sulfur ion exchange during our annealing process, in which we transform small grains, small nanoparticles, into large grains. So you can see some clear images here about the consequences that has for the morphology, and the idea is to minimize grain boundaries, increase our current transport, and also to maximize our photoabsorption in our device to increase our photocurrent. So what we did is we used the TM, which is a transmission electron microscope, to look at the nanoscale in both spatial and temporal resolution. What happens when we go through the annealing process? We basically recreated a furnace within the TM, and we look at measuring diffraction pattern and taking images through a range of temperature from room temperature to 700 degrees, reproducing as much as possible the conditions of our furnace. And two things came out from that work. The first one is, or the overall outcome is that the ion exchange between sulfur and selenium and the grain growth are two processes that are independent. And one, the sulfur to selenium ion exchange occurs first in kind of the low temperature range up to 400-450 degrees. You can see that by the position of that green line here that initially represents sulfur-rich peaks, and then the red line represents selenium-rich peak. And this process is continuous from room temperature of just above, starting at 100 degrees up to 450 degrees. And in terms of lattice structures, the change from a small sulfur ion to a slightly bigger selenium atom creates disorder, and this can be detrimental, or is detrimental, to our device process. If we carry on annealing our films, above 450, we notice that grain growth starts to happen around 450 to 500 degrees, and there's a small video here that will hopefully show you what happens. So if you follow what happens where the red arrow is, so we've got no materials, and then we are appearing that kind of grayish particle, which is the growth of a new crystal. And that's independent. That happens only at the high temperature stage. And during that phase, that grain growth phase, what also happens, if we look at the diffraction pattern, let's say at 500 degrees, we have the appearance of a spot here, which is the 211 reflection from a crystal structure, and that's indicative of a reordering of tin on its correct position in the crystal lattice, thus reducing the level defect of the zinc onto tin. So this was kind of critical as a way to possibly reducing this disorder in our device, and to show a comparison, so that temperature profile compares what happens in the TM, that's the blue squares, to what happens in our real furnace, that's the round, that's the circles. And based on our insight, we decided that we thought we needed to reduce the cooling period of our furnace in order to promote that reordering of tin cation. And we did that, and we've compared what we call the fast cool and the slow cool phase out of at the end of the crystallization period. And we found that, based on our photoluminescence measurement, that the slow cool sample have less disorder than they do if it's our fast cool. So this was good news, and ultimately that also increased the average open circuit voltage of our devices by about 50 millivolts, which represents nearly 25% if you consider those were small or fairly low efficiency. So this was the first insight from the ECATSS project. The next part was to look at the formation of the PN junction. Currently, best devices use cadmium sulfide, which is not so environmental friendly in terms of the presence of cadmium, even though it's 50 to 80 nanometer thick film. And what we decided is to replace cadmium by another material, which was indium sulfide. So the advantage of using indium sulfide is there's a much wider band gap, allowing more lights to penetrate into the absorber for photo collection. But the other advantage is that indium sulfide, due to its bound energy, creates a type 1 heterojunction with our material, and promotes a small barrier to the flow of electrons, and a large barrier for which electrons which are to tunnel, making more favorable for devices. Even more importantly, the difference, our QVOC you can see here on the graph, demonstrate that with indium sulfide the potential for a very large open circuit is greatly increased. So that should be given by that QVOC here. So that quasi-Fermi level here reflects what our potential for open circuit voltage was. So we supported that by first initial simulation. So the blue lines represent a real devices of ours that we've modeled. So that's based using cadmium sulfide layer. So we use defects that we know to have measured in our setup, in our material. And then what we simply did is replace the indium sulfide by the cadmium sulfide layer by indium sulfide, and we ended up with the red curves here and the red current voltage curve, which clearly show a dramatic increase in efficiency in current. You would expect that in voltage. You would expect that from the change in the quasi-Fermi level position, and ultimately in efficiency. So this was very, very encouraging. This is simply a 1D simulation. So we did a range of measurements on the devices with and without cadmium sulfide, but we found that they did not outperform. So indium sulfide did not outperform cadmium sulfide. And the reason was several-fold. The first one is indium sulfide layer results in a a very narrow space charge region, which in turn reduces your carrier extraction. And we can see here this is a carrier concentration as a function of depth in our device, and we can see that very narrow space charge region here. The increase in carrier concentration does not help here because it is such a very narrow depletion width. And we found that using quantum efficiency measurement both in the light, in the dark, and at reverse condition, that defects are the cause. The high concentration of defects confirm that there is poor collection, and also that some of those defects are light activated and probably appearing or being present at the interface or within our indium sulfide. And you can see here, for example, in the light defect, here the change without light and the dashed line and with light, and that's typically confirm the presence of some defects, the photoconductive defects. So we looked at further simulation based on those results, and we found that if we increase the number of interfacial defects in our device with indium sulfide, we can reduce our quantum efficiency curve and therefore reduce our efficiency overall and our open circuit voltage. So our main conclusion from this is that yes, indium sulfide may work if we can remove the concentration of interfacial defect. So we've not totally been able to do that, but what we've done is we've had a different approach. So this is a current density voltage curve for a good device, about 7%, that uses cadmium sulfide. And what we did is we took out the cadmium sulfide and we replaced it with a bilayer of cadmium sulfide and indium sulfide. So what we've been able to do here is reduce the cadmium sulfide layer from about 80 nanometer to about 20. There's still some cadmium sulfide, and that allows us to increase the efficiency, notably both the voltage and the short circuit current, so that now we reach around 7.8%. Accounting for grid area, I think this is going just over 8%. So this is an intermediate step, but a step in the right direction in terms of reducing cadmium. And the final part of our work was on looking at replacing or looking at alternative substrates, and we decided to use molybdenum foils for that. And we've employed two strategies based on the work, and this is a really brief summary. So the first one we've decided to look at strategy where we can reduce the number of layers and processes in our process. So we decided for this work to not use barrier layers in our materials or in our device, and we use high purity MO foils. Because technically molybdenum is used as our backing film, as a back contact film. So the first part of the work, we spent some time understanding how we can reduce series resistance in our devices, which were caused at the interface and the excess selenium consumption into the molybdenum foil. So we managed to do that by applying a thin evaporated molybdenum films, and that was fairly successful. And then the second part of the work was to look at how we can introduce sodium into the device, because sodium is known to improve device performance, improve crystallization, and we've been able to do that by doping not during the sterilization process or afterwards, but during the nanocrystal ink preparation. So this is this was fairly novel, and this is also actually highly straightforward and very successful. And as a result of both of those combination, we've been able to make devices around the 4% plus mark, which on foils I believe are still world leading. So this was an extremely brief overview. I've really skimmed over the results, so hopefully that gives you a flavors of what we've been doing, and some of those activities are still ongoing. We have produced a range of outputs from the projects which are listed here and are available from the NECEM website. We also successfully secured several grants, and Most of those grants are around the solution processing and the manufacturability of our device and materials. And all of those projects are still ongoing. Thank you very much.